Okay, in this video I'm going to talk about the washer method. So the washer method is much like the disk method, but if you think about the area of a washer, okay, so if I had a washer, that's just an object where I have a circle and then I have a circle missing on the inside of that. Okay, so that would be a washer. If I think about the area of a washer, I have the area of the outside circle. So if I think about whatever my outside radius would be, so I'll just call it outside radius. All right, if I take the outside radius and I square it and I multiply by pi, that would give me a disk, right? That would give me a solid area. But if I subtract away the area of the inside circle, which would be the inside radius squared times pi, then that's going to give me the area of the washer, right? So it's essentially the same thing, but as a disk, but I need to subtract away the area of the inside circle. And so what you're going to see here is first of all, we're going to factor out a pi from this. So I'm just going to have the integral of the outside radius squared minus the inside radius squared, pi out front, and then dx or dy, depending on which way our washers are oriented. So I have the area enclosed by x squared and x, which would be this region right here. By the way, and I haven't really mentioned this a whole lot yet, but if you didn't have the graph, if you were not given the graph, you didn't have a graphing calculator, and you were trying to figure this out, you would need to figure out where the two graphs meet. So you would need to know when is y equals x squared equal to y equals x. That's something that we can practice later, but the algebra there is I would take x squared and set it equal to x, and I would need to solve that, and you should be able to figure out that they do cross at 0 and at 1. That's something that's going to be important, that you can figure out those intersection points. Okay, so just like before, I'm going to replicate this about the axis that I'm rotating about. So it's about the x-axis. I'm going to try my best to do this second part. Okay, so we rotate this about the x-axis. It gives us this other area. And we have this as a three-dimensional shape, right? Three-dimensional shape. So I want to think about it as being trying to find a volume of a three-dimensional shape. But what you'll notice here is that if I were to revolve this about the x-axis, I would get this three-dimensional shape that has the inside kind of cut out of it. Okay, so on the outside, this shape looks like a perfect cone, right? I've got these straight line edges to this point. I would have a cone shape on the outside, but on the inside, I've got these curved sides that go down to this specific point down here. But this is all empty, right? It's hollow inside of here. And so why is that a washer instead of a disk? Well, if I, again, were to slice this, and slice it from 0 to 1, what would those things look like? Well, if I were to slice it right here, I would have this circle where I would have, some thickness to it out here, but then I would have a hollow circle on the inside of this where those two functions, where that function is. I don't have any area underneath that second line. So I've got an outside circle, subtracting away an inside circle, and I'm going to add all those areas up. So essentially at that point, it's just like a disk, but make sure you subtract away the inside part. So when we set up the integral, again, we're going to think about which way are we slicing this. So we're slicing it vertically, which means we're going to stack them from 0 to 1. I'm going to take the pi out front, so that takes care of the pi for both of these in doing so. So I just need outside radius squared. Well, my outside radius, I would go from 0 up to the top function, which is y equals x. So I'm going to have x squared minus, I'm going to subtract away the inside radius squared. The inside radius squared would just be from 0 up to y equals x squared. So I would have x squared squared dx. And that's how you set that up, and then it just comes down to simplifying and integrating and evaluating at that point. So x squared, let me get rid of that. X squared, so it'll just be x squared, and then x squared squared, I want to multiply those exponents, which should give me x to the 4th, and then dx, and we're ready to integrate. So pi times 1/3 x to the 3rd minus 1/5 x to the 5th, and I'm going to evaluate that from 0 to 1. So if we plug in 1, we get 1/3 times 1 cubed minus 1/5 times 1 to the 5th, and I'm going to subtract away. If I plug in 0, I'm just going to get 0. So at this point I just have pi times 1/3 minus 1/5, 1/3 minus 1/5. If I get a common denominator of 15, that'd be 5/15 minus 3/15, which would be 2/15, and I multiply that by pi, which would give me 2 pi over 15, and again that would be units cubed because it is a volume. So again, just like the disk method, I'm slicing these things either vertically if I'm going over a horizontal line, or if I'm going over a vertical line, I would slice them horizontally. I would do the top function as my outside radius. The inside radius is going to be the bottom function. If I were slicing these the other way, so I'm just going to talk about this really quickly instead of doing a separate example on this. But let's say I were revolving this about the y-axis instead of the x-axis. Well, that would give me this shape right here, where my line is on the inside and my parabola is on the outside. Okay, and I would slice it, and my circles would go like this. My circles would be oriented this way. Okay, well, if that were the case, first of all, my integral would still be 0 to 1, but it means 0 to 1 as y coordinates, from 0 to 1. And my outside radius is going to be the outermost function, which in this case would be x squared, and my inside radius would be y equals x. And so the one thing that you'd want to do, and so it's not as easy as just flipping these things around, the one thing that you would need to do in that case is, because my radii are oriented horizontally like this, I would need to change these functions into not y equals x, but think of it almost as x equals y, and not y equals x squared, but to think of that as x equals the square root of y. And then my integral, if I were to set that up, I would still have pi, I would still go from 0 to 1, but if I'm slicing this way, just like with the disk method, if you slice it this way, it needs to be in terms of y. Same thing with the washer method. So my outside radius, I said, was x squared, but I want to think of that as the square root of y squared minus y squared, and that's going to be dy. So if I were revolving this about the y-axis, this would be the integral that I would get to find the volume of that shape, which is different than what we did for the volume going about the x-axis. Okay, so just keep that in mind. Things can change if you revolve that around the y-axis or a vertical line. Instead of doing a separate video on that, I'll just relate how that looks compared to the disk method when you do that. It's very, very similar.